My name is Pooi See from the School of Material Science and Engineering, Nanyang Technological University in Singapore. It's my pleasure to be given an opportunity to share our work that's related to deformable electronic and energy devices for a human-machine interface. So in this talk, I'd like to highlight the progress related to deformable materials for energy and electronic devices. Not only it can be used in consumer electronics, it can also be operating and functioning in many emerging applications, such as soft robotics, augmented intelligence that relates to IoT for agriculture monitoring, human healthcare, as well as wearable applications. In view of this landscape, our group has been active in developing materials for deformable conductors that leads to human-machine interface. And these two applications of soft receptive devices and soft responsive devices both culminated to the development of the emerging human-machine interface. And many different applications, such as receiving the stimuli from environment based on pressure, temperature, strain, and touch sensors, while providing the output to the users through coloration changes in electrochromics or lighting, such as electroluminescence, as well as the haptics development that uses actuation that provides user a type of feeling that may augment the functionality. So in our group, the focus has been primarily on using stretchable and deformable materials that has been rationally designed and synthesized, which will provide applications in energy harvesting, energy storage, and towards applications such as electrochromics. In the tribal electricity, for example, production and charges and transport of charges are very important. Similarly, intercalation of charges can also be used for energy storages in supercapacitors or alternative batteries. Meanwhile, charges intercalation into electroactive material can also lead to functional devices such as electrochromics. So therefore, let me start with the introduction of electrochromics, which is a typical electrochemical device having a cathode and anode as the transparent conductors, sandwiching an active electrochromic layer with an ionic conductor as the counter electrode. Oxidation and reduction is happening within the system when a small applied potential is incurred. And the charge conservation will lead to a closed-loop battery-like device that provides changes in color due to the changes in the material oxidation states. Examples such as the inorganic oxides, which has different coloration based on the oxidation states. And these materials can also be tailored into nanostructures to enhance the surface area to provide additional opportunity for diffusion and ion intercalations. So electrons transport can therefore be enhanced with the nanomaterials interface. With the use of nanostructures, we can then also coat these materials onto flexible substrates such as plastic or roll-to-roll coating and printing, or on glass, such as in smart building, in order to conserve energy while blocking the daylight and then saving the energy indoor. By reducing air conditioner expenditure, for example. And this application is also interesting for the upcoming electric vehicle. And we have seen here the example given is a tungsten oxide that can be intercalated with lithium ions, which will lead to a compound that portray a deep color spectra. And this coloration and bleaching is reversible upon deintercalation, which leads to the switchability of such low power devices. It can be considered as an energy saving device. Over here, the challenge is to prepare flexible transparent conductors that can work on large area printable substrates. One of our approach is preparing the silver grade that is conductive and transparent because of the large opening array and very thin silver lines that are connected to each other, providing the electronic transport. While in order to improve the electrochemical stability and oxidative resistance, a layer of P.PSS is also coated on the surface. That makes a hybrid transparent conductor that can be very mechanical durable and with outstanding flexibility. So as we can see here in the sheet resistance measurement as a function of time or a number of days, upon passivating with a top P dot layer, the conductivity can be maintained over a couple of months, whereas without the P dot, it might undergo oxidative degradation for the silver grades. And after making the transparent conductor, we print the tungsten oxide onto the layer and fabricate the device in order to demonstrate the transmittance modulation upon application of a small potential. Here shows the many thousands of cycles in optical modulation in terms of transmittance over a range of 80% transparency down to less than 5% blocking of light, indicating that this film can be electroactive controllable in tailoring the amount of light that is transmitting through the transparent layer. And therefore, it can be mounted onto transparent glass or plastic substrate when required. More importantly, the mechanical durability is good, whether under concave or convex curvature, it can still maintain a relatively stable modulation in transmittance. And the idea here is that the electrochromic can actually lead to an indicator of energy storage as well, because the amount of charges incurred can be reflected in the different degree of color spectrum. On the other hand, and explain a dual functionality where charges that is being trapped into the electroactive layer can be discharged during the night in order to provide power to the building lighting. In this case, it's a dual functionality device that makes it attractive. So on the printing aspect, improvement on the printable ink as the electrochromic active layer is very crucial. Here, we formulated the tungsten oxide nanoparticles that are homogeneous with structural sizes of less than 100 nanometer and able to be coated using inkjet printing over large area, as can be seen here in figure D. It is a substrate of more than 20 by 20 centimeter, and the performance is relatively good. Using the printing ability, we can certainly use a direct writing approach to pattern different structures very easily, adding to the advantage of an additive manufacturing without wasting a lot of materials, like in the subtractive approach, and also material waste can be reduced. So using the printing method, we believe that it will help in the printable electronics integration. And also it enables the flexible electrochromic applications because of eliminating the need of a high temperature sintering, which is often not desirable in any other coating technology that might be difficult to overcome. Using the printable ink, we can also make them onto foldable papers. In this case, we prepare a transparent paper using nanocellulose that can be casted onto a wide area. Because of the very fine structure of the cellulose that has been extracted from nature, we can see that upon casting them, in this case, a vacuum filtration method has been used. It leads to a transparent paper that is very robust, which can be folded to 180 degrees. And multiple cycles of the paper can also be attained when it has been coated with an thin layer of silver nanowires. So these silver nanowires on the surface, conformally coated onto the nano paper, leads to the development of a piece of transparent paper that is highly conductive. In order to make the nanowire to be well distributed, we also employ the spray coating approach, where spreading of the nanowires onto the substrate, including nanopaper or polymer substrate, can be achieved. So this spray coating actually has the governing mechanism of spreading and evaporation method to lead to a bundle formation of nanocoils that is formed onto the substrate. Upon drying, it leads to this network structure that has a coiled and bundled network, which leads to a very good transparency, as well as low haze and high transmittance with low resistance. So over here, very thin substrate with a small bending radius can be achieved as well. So this transparent nano paper with a conductive layer can be scalable. As we can see here, this is almost the size of a 20 by 20 centimeter piece of transparent paper that can also sustain up to 50% strain without degradation. Imagine paper are usually not strainable, but over here it shows some stretchability that it will not lead to tearing or disruption in the electronic conductivity. So example of the scalable paper is shown here. It can be rolled up at the same time, still provide the conductivity to light up the LED at the back. And it can also sustain a spillage from water or liquid, and it can be crumpable and still maintain the electronic conductivity. The use of the nanocellulose creates an interesting avenue for us to explore different options on how to incorporate them into textile energy application. By esterification and addition of oleochlorate, after the nanoprecipitation and transfer into a polar solvent, we convert the nanocellulose into an nanoparticle form that has the ester group on the surface. With that, these nanoparticles can be spray coated onto different substrate. At the same time, it endows it with a hydrophobicity. This hydrophobicity is very useful because it can protect a lot of new materials from undergoing degradation or absorption of moisture. One example is the 2D black phosphorus material, which has very good performance, electronic semiconducting property. However, the pain point for black phosphorus is often the degradation, photooxidative degradation. And we have now used the particles to protect the black phosphorus in providing a stable bilayer structure. So this bilayer structure can be introduced onto textile wearable device in order to fabricate a textile energy harvester based on a triboelectric mechanism. In the triboelectric mechanism, it is based on the charge harvesting from the surface through a contact mode, frictional mode, or sliding mode. So in this example, it is by compression mode. And the use of the black phosphorus as the charge trapping layer have enhanced the property of charge density that is incurred during the contact mode that leads to a high voltage output as a function of time. It also shows a very good durability. So the function of the coating here is basically to enhance the surface potential. Like I explained, the black phosphorus has the ability to trap the charges, and therefore it can synergistically work with the cellulose particle, which leads to an enhanced surface potential, which suppress the charge loss during the contact separation mode. Controllable surface potential can be achieved based on the amount of coating content as a function of concentration or loading amount, which is tunable as shown here. So as a result, the power density is in the range of 0.5 milliwatt per centimeter square, which is very good, which can provide charging to a capacitor and leads to a powering up of electronic gadgets just by mechanical tapping without any energy harvester. So over here, the use of a stretchable conductor has to be considered if we're keen in developing wearable electronics. So one of our earlier attempts is to use an elastomer with silver flakes, which does not give very good cycling stability and stretchability. It often leads to an increase in the resistance, let's say at 300% strain as shown in the red curve over there. This is because the silver flakes will tend to dissociate upon a high stretchability. So we thought of the hypothesis of adding a liquid metal which can serve as anchoring particle between the silver flakes so that upon stretching, these liquid metal particles, which has an encapsulated oxide shell, could be broken and release the conductive liquid metal to mitigate the increase in the resistance. Indeed, this works very well. It works not just for flakes, particles, but also the nano particles of silver with the addition of liquid metal. It shows very robust stretchability up to 800% strain, and the resistance increment is rather stable. Although there is a gap between relaxed state and the strain state, but it's very stable. The gap is due to the irreversible loss in the electrical conductive pathway of the silver flakes, which are not anchored by the liquid metal. So this approach allows us to make a highly stretchable device. An example is the highly stretchable triboelectric device as shown here, where preparation of an elastomer which can serve as a triboelectric active layer, it's very crucial. Based on the hydrogen bond in the polyurethane acrylate material or elastomer, it creates the possibility to do that. And we also introduced functional groups such as HEMA in order to tailor the cross-linking density and provide multiple types of hydrogen bonding in the polyurethane acrylate. So this HEMA-based or HEMA-grafted PUA has a very high stretchability as shown in the stress strain curve and multiple cycles with very low hysteresis. And more interestingly, due to the hydrogen bonding, it has a good self-healability as shown in the figure on right, where upon healing, the mechanical property can also recover to a certain extent. And in this polymeric matrix, the hard segment always serves as a thermal reversible crosslink, which controls the stiffness and elasticity, whereas the soft segment will be used to tailor the self-healing property, as I mentioned just now, and it also allows a certain enhancement in the toughness. Using this elastomer and coupled with our liquid metal stretchable conductor, we can actually prepare a fully stretchable triboelectric energy harvester. In this case, the harvester is made of the polyurethane acrylate, as mentioned, with the counter contact of a latex or any other contact like aluminum PET as well. So it works well, and it also leads to not just stretchability, but self-healing ability. So the healability is shown here with a cut or so-called bifurcation. We can see obvious physical damage, but under a certain thermal budget, the self-healing of the material can be fully recovered, which includes the electrical and mechanical healability. So having the elastomeric material is useful, but we would like to have chemical interaction between the elastomer and the liquid metal particle or the metallic flakes that we have introduced. So in this case, we thought of modifying the urethane material with a functional group of carboxylated because it provides then abundant hydrogen OH hydroxyl group with the incoming fillers like metallic conductors. So with this approach, we introduce the nickel flakes, which are more stable for electrochemical applications. And indeed, it works well where the carboxylated PUA elastomer leads to highly stretchable and healable electrochemical active conductors. So as shown here, there is the hydroxyl group that's interacting with the fatty acids on the surface of the nickel flakes. And this leads to a good physical anchoring and chemical interaction at high strain for energy storage applications. With the addition of liquid metal, we also study the electrochemical stability, both in the aqueous electrolyte in figure A and the ionic liquid in figure B. As we can see here, the liquid metal is not very stable in aqueous electrolyte. Whereas in the liquid metal, on the ionic liquid environment, it creates a highly stable electrochemical performance, which makes it interesting for a high stretchable electrochemical energy storage that is also healable. So the healability of the current collector in the battery is shown here, which recovers 100% of the stretchability and electrical healing efficiency of 75%. Upon the full fabrication of the energy storage device, we can see here the performance in terms of strain. It is about 200 to 300% strain, and multiple stretching release cycle of the stretchable battery can be attained. And for the use of ionic conductor in the transparent energy harvester, we have employed first hydrogel, which has abundant water that creates this network that is highly transparent and also contains a lot of ionic species. And it is a very good self-recoverable material as well, with the ionic base, the material that has a high self-healability. And we can see here the transparent energy harvester is almost like a transparent skin, and then it can harvest energy through the mechanical motion, and it is highly stretchable. So by simple tapping, for example, without any energy source, it can power up the digital watch as indicated in this demonstrator. And not only that, we also work on printing the ionic gel to create a transparent array of touch sensors that can operate during a dynamic bending and stretching condition without affecting the touch sensing signal. And this is due to the innovative coplanar interlocking diamond layout, which suppresses the strain-induced artifact when it augments the sensing performance. So we have summarized our work on these ionic and electronic conductors for energy applications in the published review over here. And more recently, we also provide additional insights on how can we improve the energy power density and provide strategies in integrating all components in a self-driven integrated system. So with that, I would like to summarize our work, mainly through the synthetic electroactive material design. We realize soft devices through flexible transparent conductor, super elastic liquid metal stretchable conductor, and ionic gel conductor. We envisage that the next generation integrated device would be very crucial and require augmented materials, functionality, as well as integrated device strategies. So with that, I thank you for your attention, and I also acknowledge my co-workers as well as the funding agencies. Thank you.